Good afternoon, bon après-midi. Welcome to this edition of the Physical Society Colloquium. I'm coming to you live from the brutalist majesty of the Rutherford Physics Building at McGill University in beautiful downtown Montreal, where we explore new horizons, including studies of holes, black and otherwise. If you're in the Zoom session and you prefer not to be recorded or live streamed, please log out of the Zoom session and join us via YouTube. This afternoon, we will have a 45-minute talk followed by 15 minutes of questions and answers. To ask a question in Zoom, please use the raise hand feature following the talk. To ask a question in YouTube, please enter it into the chat. The questions will be relayed to me by my sidekick following the talk. If you have a question during the talk, please feel free to enter it into the YouTube chat or into the Zoom chat, and I will try to raise the question to the best of my ability during the talk. After the Q&A session, the live streaming recording will stop. Professors will be asked to log out of the Zoom session, and undergrads, grads, and postdocs, as well as other non-faculty in the Zoom session, will be invited to the après colloque, a chance to get to know the speaker in a more intimate setting. With that, I will now pass to Professor Daryl Haggard to introduce the speaker. Daryl.
Great. Good afternoon, everybody, and welcome. It's a pleasure to have everyone here. And it's my really, truly enormous pleasure to introduce Professor Feryal Özel, who is coming to us from the University of Arizona, where she is a professor of astronomy and physics. Professor Özel is also co-PI of the Black Hole Partnership for International Research and Education, a founding member and member of the Science Council for the Event Horizon Telescope, and the chair of the LINX Science and Technology Definition team. So I'm a little worried about digging in too much to Professor Özel's talk to just tell you about how amazing she is as a scientist, but let me just highlight that she's worked a lot on theoretical models for neutron stars, in particular put some incredibly important constraints on the neutron star equation of state. She's also worked very hard to help us understand what images of supermassive black holes might look like from a theoretical perspective, and hence informed all the very, very exquisite work that you've seen from the Event Horizon Telescope recently. Professor Özel did her undergraduate degree at Columbia University and a master's at the Niels Bohr Institute, where she also spent some time working at CERN. She did her PhD at Harvard University and was a NASA Hubble Fellow and also fellow at the Institute for Advanced Study at Princeton after completing her dissertation work. She's a fellow of the American Physical Society, a member of the Science Academy of Turkey, and also does a lot of work doing sort of science advising for the US government through an entity called JASON. She's been awarded multiple prizes through the American Physical Society, the American Astronomical Society, and also as a part of the EHT, some really fantastic acknowledgement of that beautiful work through the Breakthrough Prize and the Rossi Prize, among others. So without further ado, let me please ask you to help me welcome Professor Özel today to tell us about her incredible work on black hole physics at the horizon scale.
Thank you so much, Daryl, for this nice introduction. Now I have to live up to it in my talk. I was hoping you would just really lower everyone's expectations. So if I don't deliver, that would be okay. And thank you, Bill, for setting all of this up. It is my pleasure to be with you this afternoon. I wish I could visit in person, hopefully soon, but I will do what I can from a distance to tell you about some of the black hole physics that we've learned about at the scales of the event horizon of the black hole. I'm sure you've seen this image. I will try to give you a little bit of the background for the Event Horizon Telescope, but then focus more on the recent work that we've been doing. So what is the Event Horizon Telescope? A quick reminder that it's not actually a single telescope, but a network that spans the globe. It's a bunch of telescopes that are capable of observing light at 1.3 millimeters. And we need the global coverage in order to increase our angular resolution. The more separated that our telescopes are, the better angular resolution we have. So in 2018, we had these stations that you see on the map. And since then, we've been steadily adding some more. For example, there is now a second telescope in Arizona, 12 meter on Kitt Peak, and there is NOEMA that's being added to our array as well. So what do we do with this array? Well, we use, as I said, we are trying to increase our angular resolution. And when the telescopes are physically separated from one another, what we do is use a technique called aperture synthesis interferometry. What that involves is taking telescopes and looking at a distant object. In our case, it's going to be distant black holes, simultaneously. So whatever signal is coming in towards the Earth, it's being recorded by 2 or more telescopes simultaneously. And basically each incoming wavefront is time tagged with exquisite precision. So we use hydrogen maser clocks to do that. The data get recorded on hard drives, and then these hard drives are then shipped to centers that correlate these data, which means combining and finding the overlap between these incoming signals. So once the data are correlated, then we can use it as if it was collected by telescopes that are by a telescope that is as large as the separation between these 2 telescopes. Obviously not the collecting area, but the angular resolution that it affords us. To tell you a little bit more about this technique, because it's crucial to how we make the image that you've seen, what each pair of telescopes at any given moment will do is give us one Fourier component in the 2-dimensional Fourier space. So let's say that we are looking at this telescope and this telescope, looking at an object in the sky, separated by this baseline length L. What that will give us is a single point in the Fourier space. If this is north-south, this is east-west, that is as large as the separation between the telescopes divided by the wavelength of the observation. The technique is very similar to medical imaging, for example, doing a CAT scan. And as we know maybe from CAT scans, if you've ever had it, the idea is that the machine then rotates around you and gets a look at you from various angles and uses these different Fourier components in order to synthesize an image. That's why we call this aperture synthesis interferometry. Well, what do we do when we're looking at a distant object? What we do is, since we can't rotate the object or we can't rotate around the object, we rely on the rotation of the Earth instead. So as these baselines rotate, they look at the object in the sky from a slightly different angle. And then we have different baseline pairs that start filling out this Fourier space. And as you get more and more information about the underlying image from filling the Fourier space, then you can ask yourself, what is the underlying image that I have looked at? So to make this a little bit more visually concrete, let me show you what we've done in the 2017 campaign of EHD. Our primary targets were a galaxy in the Virgo cluster called M87, Messier 87, which was for a long time, and I mean almost a century, thought to harbor a supermassive black hole at its center. The reason we think that is because it has this jet feature, this collimated outflow of gas associated with the center of the galaxy that we think is powered by accretion of gas onto this black hole at the center. And from various estimates, we thought this black hole was of the order of 6 billion solar masses. So it's a good target because even though the Virgo cluster is far away from us, because the black hole is very massive, we thought it would have a large, nice angular diameter in the sky that we could resolve using this interferometry technique. So we set up our telescopes. It took us more than a decade to outfit all those stations that I showed you. And in 2017, we had our first observing campaign. You see a lot of blue in these pictures. That is a good thing because even though 1.3 millimeters can be done in principle during the day, so it's not, it doesn't require nighttime observing, for example, it does not do well with high moisture content in the atmosphere. So you really need clear skies to observe at 1.3 millimeters as well. So people are happy, everything is blue. So we went ahead and collected data on M87 as well as on a few other objects, including the supermassive black hole at the center of our own galaxy that we call Sagittarius A star. While we were building the telescopes, we also accumulated a whole bunch of people. This is not even the whole collaboration. This is just from a meeting in 2018 that we had in the Netherlands as we were getting our results ready for publication. All that went into making the donut that you've seen. We loved the memes that came out, and it was all good. Why does it look like a half-glazed donut? So the rest of my talk is going to be about why we think the image looks like this donut here. What of the image characteristics can we really trust? And what does that tell us about properties of black holes and of the accreting gas around the black hole? So I already showed you the Fourier space. So this is the exact same plot that I showed you as the baselines rotate, and you get a look at the image in the sky from different viewpoints. So this is the north, south, east, west. And the only difference here is that different telescope pairs are now color-coded on this Fourier space data. In principle, the image does not need to have azimuthal symmetry. And while we truly image it, we don't rely on azimuthal symmetry. However, just for understanding what of the Fourier components of the image tell us about the underlying image, what I want to do here is collect all of these in all different azimuthal directions into just the spatial frequency. So how far is the separation of each of these baselines? Put that on the x-axis, and the amplitude that we measured on the y-axis here. So that's called our visibility amplitude. The thing that jumps out at you, and the thing that jumped out at us, is that the Fourier transform of this underlying image has this ringing structure, right? There's a maximum here, there's a minimum here, a second maximum, and probably heading towards a second minimum. When you see a ringing structure like this in a Fourier transform, you immediately think this is a Bessel function, and Bessel functions represent disks or rings in the underlying image. So it's a telltale sign that you're dealing with basically sharp edges, but it could be a disk. So how do we model these data? I will show you a toy model. This is not actually how we do things, but I think it helps increase one's confidence in really understanding why we see a donut and not, for example, a disk like this. So what I have here is the image space on the left-hand side and the corresponding Fourier space on the right-hand side. This is, for astronomers in the audience, this is 50 microarc seconds, so a tiny, tiny angular size in the sky. Let's say that this is our image of a disk of arbitrary size. These are now all the data points in red, and the green is the Fourier transform of this trial image that I put on the left. You look at this and you say, yes, I see some ringing, but you're doing terrible in terms of describing this data. What can you change? Well, the first thing I can change is the size. And the size determines the location of this first minimum. So by making it a little bit larger, as you see, now these data points are described well. But we're still doing pretty terrible. I mean, obviously, we are not getting any of this. The only other thing we can change is the width of the ring compared to its radius. So the size measurement and the fact that there is a hole in the center, that there's a real, genuine brightness depression in the center is right here. Like you can see why we felt confident in saying that there is a hole in our image. If you look at this carefully, it's still not doing a great job. So the only other thing that we can do is realize that our telescopes don't have infinite resolution. Even our largest baselines to the South Pole, to the North Pole, etc., have a finite resolution. So if we now blur this image to the resolution of our telescopes, that immediately describes those data points better as well. So in a nutshell, this is how you go from data in Fourier space to inferring what the image looks like. As I said, this is not really what we did, obviously. This is a toy model for visualization purposes. However, we did fit to the data a large range of analytic functions, as well as things that are not analytic functions. So we literally divided up the image space into pixels. So built a brightness model that is based on pixels. Just like I put a trial analytic function, we can now put a trial image here with some brightness on some pixels, etc. And we can effectively minimize a chi-square-like value, which is defined in the normal way, with the addition of some regularizers. A regularizer basically allows for the fact that we don't have so many data points that we can have truly independent constraints on the pixel brightness of so many pixels. So there are some penalties for rapidly changing nearby pixels, for example. So some regularizing in the image space. This trial image gives you this green curve that you're seeing, bluish green. Again, not a good fit, but let's do this minimization procedure. And now, since we are not assuming azimuthal symmetry, we can actually take these different cross sections at different azimuths. And you can see that in one direction, there is a nice minimum because it's symmetric in brightness in the east-west, whereas in the other direction, these data points come from the fact that there's quite a bit of image asymmetry in the north-south direction. Okay, so we've done a variety of these in order to understand what the underlying characteristics of the image are. The way I would summarize what those underlying characteristics are is that first and foremost, we are seeing a narrow ring of emission that we are associating with the plasma surrounding the black hole. So gas is being accreted in the process. It heats up, it emits radiation at 1.3 millimeters, it's synchrotron radiation. And that's what we are observing with our telescopes. So we see a ring-like structure coming from that. The second thing we say is that, look, there is a hole in the center and that we're associating with that hole with the black hole shadow. I will explain what that means. And then the third element that we can stand behind, as you've seen from the image reconstruction, is that there really is a north-south asymmetry. This is expected because the gas swirls around the black hole at speeds that are basically becoming comparable to the speed of light as it gets closer and closer to the horizon. And what that does is introduce Doppler shifts. So let's say that the black hole spin axis was in this direction on the screen. What that means is that the gas in the top part would be rotating away from us, and the gas in the bottom part would be rotating towards us. And that is the part that's Doppler boosted and it's brighter, and the top part is Doppler deboosted and therefore dimmer. So we don't know a priori what the black hole spin axis for M87 is, but what we do know is that if we interpret this brightness asymmetry as aligning with the angular momentum axis of the black hole accretion flow and the spin axis, that it aligns with the direction of the jets that we see from the source. So a very nice, basically consistency check as far as how to interpret this image. So we have done, as I mentioned, many different analyses of this by fitting different analytic models, by doing different types of regularizers. What I want to show you here is a quantitative. So this was basically qualitatively what we see in the image. Quantitatively, what we see is that if we plot the fractional width, how thick is the ring allowed to be? as a function of the diameter of that ring. These are the various reconstructions that you see. They are anti-correlated for reasons that are well understood in terms of the Fourier domain measurements. And this is the effective resolution of the EHT beam. So anything above this is blurred at this resolution. Anything below this is model fits that don't require that blurring. So what we get from both of these modeling techniques is that we can measure an image diameter with uncertainties, and we placed it at 42 plus or minus 3 microarc seconds, and a ring with as an upper limit of 20 microarc seconds. And you see that that's a pretty conservative upper limit that is up here. Okay, so at this point, let me just go back here really quickly. Having made these measurements, what can we do with it? We like to learn some physics from it. My talk is entitled Physics at the Horizon Scale, and that leaves you with a choice that you can make. It's basically a crossroads between, do I want to understand the black hole spacetime better? Am I interested in testing general relativity in this environment and understanding things about horizons? Or just as valid, do I want to understand the enormous range of physical phenomena that happen in the plasma that is surrounding the black hole? It's very rich. Accretion physics is very exciting in many fields of astronomy, many subfields of astronomy. And I will explain what this means, general relativistic magnetohydrodynamics. So we're at a crossroads. If I want to understand the space-time, I want to go in the direction of what is the minimum I need to know about the plasma. Or I can say I want to understand all its glory. So the reason we think that an image like this can be used to understand something about the space-time without relying too much or too strongly on what you understand about the plasma is that GR has some characteristic radii that are associated with the presence of a black hole that gets imprinted on an image like this. So in the rest of my talk, I'm first going to take the road on the left. I'll say, what are these space-time characteristics and why do we think we see it in these images? And time permitting, I will then take the second road and say, wait, there is a lot more that we can understand about the accreting gas itself. So a 2-minute tutorial on what GR says about spacetimes of black holes. As I mentioned, there are some characteristic radii that are well defined and that actually play an important role in the formation of an image near the horizon. So first of all, this is the Boyer-Lindquist radius, so in units of the mass of the black hole as a function of black hole spin. And the 3 characteristic radii that we are interested in are the location of the event horizon itself, so from 2m to 1m, as you go from non-spinning to maximally spinning black holes. But the one that is more important than the horizon is the photon orbit. This is the location where photons with tangential velocities can actually complete full circular orbits multiple times. And of course, it's unstable, so some of them will fall in, but some of them will actually come out and reach an observer at infinity. So this is really the separatrix between things that all the light that goes in and the light that can come out and reach the observer. There is a third characteristic radius that is of importance to the gas, not so much for the image itself. This is the location where matter can have stable circular orbits, so it's called the innermost stable circular orbit, or the ISCO. And for co-rotating and counter-rotating accretion flows with respect to the black hole spin axis, it possesses this range of radii. So with this in mind, let's delve a little bit more into which of these play a role in making the image. I'm showing you now the photon orbits for spinning black holes. This is an animation borrowed from Leo Stein. Black hole spin parameter of 0.4, black hole spin parameter of 0.9. What you see is that the photon orbits precess, but they trace out these very nice spherical surfaces around a black hole. So in GR, the photon orbit is not just at a particular location, given a black hole spin, but it is also guaranteed to be a circle, or a sphere, if you look at it as a surface. So if you look at it as an image, what we are saying is that let's mark these interesting locations. Let's mark the horizon with red and the photon orbit for the non-spinning black hole in this blue circle. And what is an image? It is a collection of the light that is emitted from different impact parameters. So the path of the photon that comes from the black hole or surrounding the black hole out to an observer at infinity is going to be given by this line in black, and the impact parameter is marked up here in the legend. So let's change this impact parameter. What you will see is that as we change it, the paths that the photons follow in the space-time of the black hole and get mapped to the image that we make at infinity follow a very characteristic deflection angle. So this is just gravitational lensing, so that if I now stop the animation and put it all together, what you will see is that things that are inside of 5m, as we see them at infinity, actually are absorbed. So these are the ones that cross the horizon and fall in. The things just outside of 5m are the ones that are going to be the brightest because they have the longest path length. You can see all of these get mapped to this little part of the image. And as I go further and further out, again, these are going to be relatively long path lengths that contribute to the image. So when I look at something at infinity, the brightest part is going to be right around a lensed radius of 5m in geometric units. Obviously, as you go along these paths, you also pick up exactly how much emission there is at these different locations along the path. So we're not saying that the plasma plays no role, but given that the plasma gets hotter and denser as you come closer to the black hole, and that the path length increases, the brightest part of the image basically ends up surrounding this the photon orbit that I had mentioned before. The other nice thing about GR is that, as I said, it not only gives us the location, but also the exact shape of the black hole shadow. So if the image is following the shadow, then what we expect for the symmetry characteristics of the image are going to be linked to what we expect for the symmetry characteristics of the shadow. What I mean by that is when we change the black hole spin or the inclination of the observer with respect to the black hole spin axis, what you will see is that there is an apparent displacement, but the shape remains a circle. So GR makes the prediction that until very extremal spin parameters, this shape is going to be circular. So this was quantified in earlier papers. The average radius of this circular shape, and if it deviates from the circularity a little bit, that's what the average radius indicates, as a function of black hole spin and as a function of inclination angle, spans a very, very narrow range of uncertainties, so plus or minus 4%. So if I can now use the image to get the the location of the shadow, that tells me exactly what the mass of the black hole that is responsible for that is. Okay, I have very little wiggle room, like no free parameters in GR. But if I go non-GR, and there are many, many extensions of GR, both in terms of some motivated individual theories, and more importantly, in terms of metric deviations from Kerr that allow you to explore a parameter space that is wider than the predictions of general relativity. For example, this is the Johansen-Psaltis metric, this is the MGBK metric. What we are showing here is that if you do allow yourself to deviate from GR, then you have a freedom as far as what the shadow size can be. So while GR has no free parameters, the minute you expand the range of possibilities in terms of the metric around a compact object, like a black hole, then by changing these parameters, you can certainly change the size of this shadow by very large amounts. And you can also change the deviation from circularity by quite large amounts. So we've looked at shadow size as a function of perturbation parameters and showed that they can deviate a lot more strongly. The weak dependence on the black hole spin persists, but it is calculable in each of these different extensions of general relativity. Furthermore, in a recent paper, we've also noticed that the parameters that affect the shadow size are all in the time component of the metric when it's written in aerial coordinates. So that gave us a more direct way of comparing the results that we get from black hole images to other tests of general relativity. So putting all of that together, what we are saying is the following: that the images, the bright part of the images that we see, trace the shadow of the space-time, and therefore they can be used to measure the size and the shape of this shadow. So these are 4 different representations of simulations of the gas around the black hole. I will come back to this point, but what you see is that the photon ring and the surrounding plasma always trace out the outline of the shadow. So if we measure the image diameter, calibrate that diameter to the shadow size, and then using this GR relation that allows for this uncertainty in the spin and the inclination angle, that size will map to a unique black hole mass. We've done this for the image that we obtained with M87. I showed you this before. I showed you this part before. And now let me go ahead and show you the rest of what this image diameter and ring width imply in terms of the properties of the black hole itself. It's from the imaging only, it gets a mass of 6.5 billion solar masses with an uncertainty of about 1 billion solar mass. When I started the talk, I said M87 was chosen as a target because we thought for a very long time that it harbored a supermassive black hole, and we know its jet properties, etc. And we had an estimate of its mass by looking at the dynamics of stars around the black hole. So just like we can solve the Kepler problem, look at things moving around a central mass, and by watching their orbits and velocities, determine how massive the central object is. This is something we do regularly for black holes. And we were able to, because of this, compare the mass that we are getting under the GR assumption to what was measured before. The blue curve here shows the posterior that comes from the stellar dynamics for the mass of the black hole. There is also a measurement by looking at the dynamics of the gas at large distances from the black hole, not at the horizon scale that we're doing. And as you can see, there is a discrepancy between the two. So we said, okay, let's go ahead and compare our results to both of these. And the HT measurement was smack on the stellar dynamics measurement for the mass. And it disagreed by a factor of 2 approximately with the one from gas dynamics. So now if we take this as our prior measurement and ask ourselves, how much do we deviate? We deviate, well, the deviation parameter peaks at 0. So basically the same central values with an uncertainty of about 17% coming from our errors as well as the error in the mass uncertainty here. So our conclusion in the initial set of papers was that the mass measurements agree to within about 20% or 17% more precisely. In recent work, when we started looking at these parametric extensions of the Kerr metric and really quantifying what shadow sizes and shapes they predict, we were then able to use this measurement even further and not just say we are consistent with GR to within 17%, but we started being able to rule out large parts of the parameter space in these modified Kerr metrics that predicted shadows that are incompatible with the data. So again, this is just as an example, one of those parameters in the JP metric as a function of the spin of the black hole. And we were able to rule out all this region that is shown in gray here. You might wonder, well, did you actually learn something new, or were these parts of the parameter space already ruled out by other tests of general relativity? Well, the only other tests that are sensitive to parameters like the one that I'm showing you here are some solar system tests, and in order to compare our results for the Kerr metric with what we learned from solar system tests before, we use something called the post-Newtonian expansion. And if you map this parameter to what we would have learned from solar system tests, it is better by a factor of 500 compared to any previous test of this term. So yes, it is a brand new region of parameter space that we are able to rule out that where GR hadn't been tested before. Let me also compare it to what LIGO tells us. Obviously, there's a huge difference between what LIGO is doing and what the Event Horizon Telescope is doing. In LIGO, it's dynamical spacetimes. For us, it is static spacetimes, and the masses are also different. I see Bill is trying to get my attention.
A quick question
yes,
in the chat
absolutely.
from Professor Jim Klein. Can you tell us how the alpha parameters enter the metric component?
In a complicated way. The only thing that I can say cleanly at the colloquium level is that it's in the time component. As I mentioned, there is a way of writing the metric where all the shadow deviations appear in the time component, but it is complex. In order for the metric to be regular, what we sacrifice is the complexity of the metric component. So it's large expressions. Any other questions I can answer right now?
There are none in the chat right now. If any more come up,
Okay.
please, everyone who's in the Zoom session, feel free to type them in, and I'll try to interject.
Okay. I just want to show you how it compares to LIGO. As I was saying, dynamical versus static spacetimes, stellar mass black holes versus billions of solar masses. So a very different part of the parameter space as far as tests of general relativity is concerned. But this is, again, this is now 2 PN parameter versus the 1 PN parameter in the post-Newtonian expansions, and the contours show the M87 constraints versus the LIGO constraints. So they're very highly comparable in these two very different regimes. I think I have maybe 5-6 more minutes. Is that right?
Yes, that's right.
So let me tell you a little bit more about how certain we are that we understand the plasma well. And again, I made the mapping between the space-time properties and the image that we see. But what else goes into it, both in terms of confidence in our results and in terms of the second direction that I was describing to you? What else happens in the plasma that is of interest? The tool that we've used in order to explore black hole environments and how gas accretes onto the compact object is called general relativistic magnetohydrodynamics. We solve the fluid equations basically, and including evolving the magnetic field for a variety of initial conditions, black hole spins, mass accretion rates, etc. And we solve these equations numerically. So this is what a typical simulation will look like. We'll run it for a long time until the flow parameters reach steady state. In addition to that, we want to map the properties of the flow to the types of data that we collect, whether this is images or light curves, how the brightness changes as a function of time from a source, the broadband spectrum. If I looked at it in X-rays versus in the millimeter, what would I see differently? So we've come up with basically fast ways of rendering these accretion flows into observables. And this is a GPU-based technique that we developed back in 2015 that allowed us to explore parameter spaces efficiently. So as part of the EHT collaboration, we've done a wide variety of these simulations. And this is a little image library, or actually a movie library, taking into account the variability in the flow as the gas swirls around. So from that, we concluded that in every case that we have looked at, the results of what we are concluding about GR is insensitive to the details of what is happening in the plasma. But we can take that a step further. You might say, well, you're making GR MHD simulations, which means you're assuming GR and you're solving the MHD equations. Maybe there is something you don't understand there. Maybe there are effects that you're not taking into account. Are you sure that the image really tracks the shadow? So recently we've expanded that work into covariant analytic models, basically take any reasonable velocity and density profile that could describe a black hole environment and forget the details and require only continuity and the fact that massive particles have to follow the geodesics of the space-time. When we did this, we found that indeed that for all of the conditions that you can explore in the semi-analytic way, that again, the conclusion that the ring follows the shadow still holds. The only way, and literally the only way you can break that connection between the two is if you take what I called a reasonable density and velocity profile and forego continuity. So forego mass conservation. Basically say, I'm just going to erase part of that density by hand, which is not physical. So you can do that and break the connection between the image and the black hole shadow. The other way you can do it is through short-lived lensing structures. So as matter, which is not of uniform density, of course, it's bubbling. As it circles around the black hole, there are going to be times where a bright structure like a flux tube or a density enhancement is going to cross a caustic behind the black hole. And at that point, make an Einstein ring that could be displaced from the location of the shadow, which is shown in the red here. But to show you how short-lived it is, this is actually a frame from a simulation. As soon as I start the actual full animation, full calculation, you saw that in less than a dynamical time that disappeared. So there is a way to test if we somehow caught M87 in April of 2017 in one of these special moments, which is repeated observations. We already had a time span of 10 days. Obviously, things would have likely changed in that time span, but further observations can answer that question as well. So in the interest of time, I am going to skip over the open questions. What I don't want to imply is that we understand everything about plasmas, that we understand accretion and can model it extremely well. There are open questions, for example, the role of non-thermal electrons, the role of reconnection, flaring events, which is something Daryl works on. So I have some slides that I'm not going to show right now, so we have some time for Q&A, but I will be happy to follow up in a future conversation or with whoever wants to stay around, in the sense that, as I said, there is a lot of nice work going on in terms of understanding variability properties, flares, effect of non-thermal electrons. But the takeaway message is that while there are all of these open questions, none of that affect even at the quantitative level, the conclusions that I presented to you about black holes today. So I will stop at that and take questions.
Thank you very much for a talk on some fascinating physics and some really interesting observations. If you enjoyed the talk, please write something in the Zoom chat. I'll be able to share the chat transcript with Professor Özel after the talk. If you're watching on YouTube, please write something in YouTube about how much you enjoyed the talk. I see there are a couple of questions that have already come into the Zoom chat. I'm going to try to copy paste them quickly before they pass me by. OK, there's one. If you are interested in asking a question and you're watching on YouTube, please feel free to type the question into the YouTube chat. The question will be passed to me by my associate, and I see there's already one that's come through. If you would like to ask a question in Zoom, please use the raise hand feature in Zoom. Otherwise, if you'd like to ask a question anonymously in Zoom, you're also welcome to enter it into the chat, although I may miss it because of all of the very nice things that people are saying right now. But hopefully I've got at least one of them. So are you ready for the question and answer period? Professor
Are you
Özel?
asking me?
Yes,
yeah, I'm more than ready, yes.
Excellent. Then let's get started. So I'll start with the one that came into the Zoom chat from Professor Robert Brandenberger. Where did I put it? Here. How does the rate of accretion compare with Eddington accretion?
Very good. So I have a reason to use this slide. The rate of accretion that we see in nearby supermassive black holes, like the one at the center of our galaxy or like the one at the center of M87, is much, much, much below the Eddington rate. So our best guess for M87 is about 10 to the minus 5 of the Eddington rate for that black hole. And for Sagittarius star, it's even below that. So part of what makes it possible to have an experiment like the EHT is the slow accretion rate. The flow at the right wavelength, the flow is transparent all the way down to the horizon, which allows us to image the horizon environment. If we were dealing with a near Eddington accretion flow, then it's optically thick basically at every wavelength, and we would be able to see the outer parts of the accretion flow, but not the horizon. And here, just because I have this up, one of the things that low accretion rate does, so this is m dots in units of m dot Eddington, is it increases the electron-proton thermalization time scale. So the Coulomb collisions between electrons and protons become pretty rare at this low density environment. And because of that, if there are events that inject non-thermal particles, such as magnetic reconnection or even other acceleration processes, then they don't thermalize quickly. So they tend to manifest themselves as these transient events that we can then see in the X-rays or with infrared telescopes.
Excellent, thank you. So there is a question that came in through YouTube. Let me see. And so there are people watching on YouTube from all over. The question is, could, in capitals, all caps, could you explain why stars in our galaxy move in many different directions near the black hole?
So that probably has to do with the accretion history of gas into the central regions of a galaxy. When galaxies form, they don't do it in one continuous fashion. They go through many episodes where they merge with smaller galaxies, or even equal-sized galaxies, or accrete smaller objects that forms nearby. And each of these come in with their angular momentum vector, and basically, after the merger, redistribute stars with whatever angular momentum they had prior to the collision. So in the Milky Way, for example, we see stellar streams that probably result from these multiple collisions in the Milky Way. Similarly, the way gas makes itself to the center of a galaxy is a complicated phenomena. So as new generations of stars form from them, they don't have to align with the disk of the galaxy, and they can have different directions.
Okay, thank you very much. I see there's a question from Professor Vicky Caspi. Vicky, would you like to unmute yourself and ask your question?
Sure. First of all, thank you for a really beautiful talk. Absolutely so interesting. And I'm just wondering if you can just give us a flavor for what you think the results for EHT and Sagittarius star, either what they could tell us uniquely about black holes, or will there be lessons learned from those data that could be applied to the M87, where you could answer some of the outstanding questions there?
Sure. So let me begin by saying that we still have not published the data on Sagittarius star, so I am limited in what I can discuss here. Having said that, I can make some general statements about Sagittarius star versus M87 that may be helpful. So for M87, I showed these two prior mass measurements, one coming from stellar dynamics, one coming from gas dynamics, that were discrepant. So we took both as priors and basically said we agree with one and not with the other. With Sagittarius star, that is not a concern. We resolved the orbits of individual stars. Nobel Prize for this year went to basically weighing Sagittarius A star. And through these resolved motions of stars, we know the mass of, or mass to distance ratio of Sagittarius A star exquisitely. So we have that one uncertainty removed. On the negative side, Sagittarius star has a smaller mass than M87, which means the dynamical timescales around the horizon are much faster for Sagittarius star by a factor of, the mass ratio is almost 1500. So timescales are much faster than they are for M87. So again, going back to the CAT scan analogy, you're supposed to hold your breath and not move while the imaging is taking place. Sagittarius star, when we integrate over a night, in the meantime is waving its arms and legs. So the bubbling in the plasma is happening at much shorter time scales than our observational windows as we wait for the Earth to rotate. So the variability that's intrinsic in the accretion flow is harder for Sagittarius star than for M87. And that's the primary reason why we published M87 first, even though we all thought when we started out that Sagittarius star would go first because of its nicer M/D measurement. So we are making our best, not guesses, but maybe best models and folding in uncertainties that come from these various effects. And we'll be able to share Sagittarius Star hopefully sometime soon.
Hey, thank you.
Okay, thanks. I saw a question in the Zoom chat. We'll go to that one, and then we'll go to another Zoom in-person question. So question from the Zoom chat, how do you calibrate the clocks?
How do we calibrate the clocks? They're maser clocks. I would not be able to tell you anything more than that, really. We should find out how the atomic clocks are calibrated.
Okay, now Paranjape Manu, would you like to unmute yourself and ask a question?
Sure. Hi. Thanks for the very nice talk. I wanted to ask about very light dark matter candidates, WISP particles. I've heard that they can form quantum atom states around black holes and condensates and all kinds of interesting things. They'll slow down the Kerr rotation. Is there any electromagnetic signal that you might see that might give evidence for the existence of WISPs?
Not that I know of. The types of things that we can do and we have done with M87 data is look for any evidence that there is a surface, whether this is an absorbing and re-radiating surface or a reflective surface. So if there are any modifications, whether this comes from a collection of particles or in some other theories from the existence of a surface instead of a horizon, whether we can use the brightness depression at the center to put a limit on any proper size, reflective properties, temperature, etc., of a horizon, of a surface rather than a horizon. So I'm not particularly familiar with what WISP would do, but if they have any signature that is some sort of fuzz outside the horizon or some additional emissivity outside of the horizon, any general argument we made on limits for surfaces would apply to them as well.
Okay, thank you. I mean, they're supposed to mix with real photons and so on, and maybe give off in decaying processes, give off photons at higher radii.
That's an interesting question. So specifically for that case, one could look at what modifications they would have caused in the image or even the spectrum maybe, and see if one can rule that out with the existing data.
Okay, thank you.
We have another question from YouTube. So the question from YouTube is, it looked like the image construction was being done with a frequentist maximum likelihood approach. What is the advantage of this versus Bayesian techniques?
It was a maximum likelihood method, and all our other model fitting is done with in the Bayesian. So if, for example, you say, what is the likelihood that the image represents a ring-like or a crescent-like structure, like those that we expect from GRMHD simulations, that's done with the Bayesian technique. So I don't know a priori if there are particular advantages or disadvantages to either of them, other than to show you this again, that basically these are maximum likelihoods and these are Bayesian methodologies. So the difference that you see in the inferred fractional width, again, is due to the convolution of image domain methods with a 10 microarc second beam size. So they cannot produce anything below this line. So that is not frequentist versus Bayesian, it's just what is folded into the model.
Okay, thanks very much. It looks like we're running just about up to time, and I don't see any urgent questions, in which case I think I will wrap things up. So if everyone could please thank Professor Özel once again. If you haven't done so already, write something good in the Zoom chat or on the YouTube chat about how much you enjoyed this talk. I know there have already been a lot of positive comments. And so I'll just wrap it up. Those of you who do not have tenured or tenure track positions, please stick around for the après colloque. That concludes this edition of the Physical Society Colloquium. Those thanks to those who have joined us. Please come back again next week for a talk by Mike Manfra from the Department of Physics and Astronomy and Microsoft Quantum Purdue, who will give a talk entitled Direct Observation of Anionic Braiding Statistics. Good evening, bonne soirée.